Hello, everyone. I'm Leona from Wizlogix, the host for today's WizConnect webinar. We're very honored to have the president of MindShare Incorporated, Joe Winkles, to spend his evening time with us today to present this webinar. MindShare is a technology training company in the US, and Joe has trained thousands of engineers on topics, including x86 architecture, high PCI Express, USB4, Opteron processors, assembly language programming, Intel Quick Path Interconnect, hypertransport, infinite band, virtualization technology, and many more. Without further ado, let us welcome Joe to speak about today's topic, new technology of USB4 architecture, the overview. Joe, please.
Thank you, Leona. And thank you, Wizlogix, for having us, MindShare, to come in and just go over USB4. So what I'm going to do is, let me start sharing my screen, get my presentation going here. All right. Well, welcome, everybody. So we're going to have this session. We're going to try and cover the technical information from an overview perspective in about 30 to 40 minutes, and a little bit of information on the front about who MindShare is. So let's just go ahead and jump in. If you have not heard of MindShare, so we are a technology company, technology training company that's been around for a long time, over 30 years now. So MindShare was founded in 1988, and we've been teaching technologies to a lot of the big technology companies for around the world, right, since then. So our website is mindshare.com. You might have noticed or heard of MindShare by our books before knowing that we were a training company. We offer a wide variety of courses on a lot of different topics. So showing them here, at least some of the main ones. So some of our courses are covering Intel-related architectures, so x86 technologies, both from an x86 architecture perspective as well as a microarchitecture perspective, so the implementations. And we even have some courses that are doing code optimization, so they'll have some labs associated with them. We have similar courses where we cover ARM-related architectures. We have courses covering different memory technologies, DDR4, DDR5, LPDDR, and so forth. Courses covering firmware, some of your hardware, BIOS, as well as UEFI related courses. And even these have labs associated with them, so you can actually get your hands on and work programming some UEFI drivers. We have courses covering some programming language like deep learning and AI, artificial intelligence. So those are nice, as well as Python, OpenCL, and so forth. Some of the other courses that we have, which this topic of USB4 fits in, is I/O buses. So PCI Express has been a very pervasive bus for a long time. We teach lots of classes around the world covering PCI Express, up to and including the latest version of PCI Express 5 right now. But this session we're going to be doing is covering USB4. Now, MindShare, we have a full USB4 class. It is a full 4 days in order to cover all of that material. We're only going to be spending about 30 minutes on that, so we'll kind of give you an overview of what USB4 is. We also cover USB 3, USB Type-C, which is the port that these USB standards are now using, XHCI, which is the controller for USB, and one of the popular host controllers. And one of our newer courses is CXL, right? So Compute Express Link, which is basically allowing us to do coherency across PCI Express. So we have a lot of courses related to virtualization as well, if that's something you're interested in, both from the perspective of a processor like an x86 processor or perhaps an ARM processor, but we also cover related to I/O virtualization. And then lots of courses covering different storage technologies as well. MindShare, we offer classes where we will come to your site, or at least we used to before COVID hit the entire world. But once that eases up, of course, we will come to your site and train face-to-face. We do this around the world. We also offer courses that are online, kind of like this one, via Zoom or WebEx. And another nice option that you might look into is e-learning. A lot of the courses that we teach, we have pre-recorded versions of them that are covering the exact same material, but we break it up into manageable sizes. So like a 30-minute or 45-minute modules And that way you can kind of skip through and take the modules you care about and skip the ones you don't. So you can check on our website for all of these types of topics. And we have public courses as well. So that's where anybody can sign up for one of these. And we teach it at a certain time. And because of the travel restrictions right now, we're doing these online. So anybody in the world can sign up and take these public classes. You may have heard of MindShare through our books. That's what we've been known for a long time. So we write books on a lot of the things that we teach. So like we cover books on PCI Express, USB 3. So USB 4 is still fairly new. So we are thinking about working on a book on that. x86 architecture, SATA, SAS, and so forth. So we write books on the things that we teach as well. So that's just a very short introduction to who MindShare is. So now let's go ahead and dive into why you're here. What is USB 4? Well, in this section, what we're going to be covering first is what is the problem that USB 4 is trying to solve. And then we're going to look at a little bit of the high-level view of how it's solving that. Now, one of the big problems that exists with our PCs and not just PCs, but our technology devices today, is they're all shrinking in terms of size. So we have a lot less area, both in terms to fit I/O devices, the compute components, inside our systems, but also if we want connections outside. So think about a phone or a tablet. The real estate on the device itself in order to plug peripherals or various I/O devices continues to get smaller and smaller. And the connectors that we used to have are just a little bit big. So how can we consolidate? How can we have a small footprint, but we want to be able to provide a lot of different connectivity through that smaller connector. And we're going to find that USB 4 is going to provide us a way of doing this. Now, USB 4 wasn't the first one to take this approach, but it actually originated, and I shouldn't say originated, but one of the ones that was popular is Thunderbolt. So Intel and Apple, back in 2000, I want to say it was 2011, introduced the original Thunderbolt. And what they were doing there is they were tunneling existing protocols. Some of the protocols that were very popular for connecting I/O devices from a, kind of an internal device perspective, like PCI Express is how you connect a lot of your I/O devices and systems, and video. And what they did is they support tunneling of those two protocols on a single interface. And they originally started out with the mini DisplayPort connector. But with Thunderbolt 3, we're going to find out they adopted the Type-C connector from USB. And the reason I'm talking about Thunderbolt is because USB 4 basically adopted what Thunderbolt 3 had been doing. So a lot of the Thunderbolt 3 technology was adopted into USB 4 and became the USB 4 standard. But of course, USB Implementers Forum added some additional functionality, and we're going to see what that is. But this is the approach that USB 4 is taking, is we are going to be tunneling other popular protocols through this single interface. And those popular protocols, we're going to have PCI Express can be tunneled through USB 4 now, DisplayPort can be tunneled through USB 4, and USB 3 is going to be tunneled through USB 4. And I know that sounds a little bit weird, like why would I be tunneling USB 3 on a USB 4? Well, what we're going to find out is USB 4 does not have its own data movement traffic. It doesn't exist. It is purely a tunneling protocol. So the only packets that you have that are native USB 4 are the ones for control, what they call control packets. They're used for setting up our system, but they're not for moving data. All of the main data movement traffic is going to be tunneled traffic, either PCI Express or USB 3 or DisplayPort. All right, so we're going to see how that is going to look. But all of this kind of started with Intel Thunderbolt. All right, so that's what we're going to look at, is how USB 4 is building on top of Thunderbolt to make this possible. Now, Thunderbolt, and we're not going to have a big history lesson here, but Thunderbolt 3 had been incorporating PCI Express and DisplayPort, but they were using the Type-C connector. Now, when the USB Implementers Forum decided to adopt Thunderbolt as kind of the basis for the new USB standard, they wanted to make sure that USB was kind of front and center. So USB 3 is supported by Type-C connectors. And there's an important difference there between the protocol that you're transferring on an interface and the actual port that is being connected with. So Type-C is a port. It's the physical connection, right? It's how you plug a cable or a device into a system. But the protocol you're carrying on that can vary. So the Type-C connector was originally designed for USB 3, but it does support alternate modes. And there were two alternate modes that were supported, or at least defined for. One of them is Thunderbolt 3. So you can send Thunderbolt 3 traffic, right? Which is then embedding PCI Express and DisplayPort. But whenever USB adopted Thunderbolt as a new USB standard, they wanted to make sure that USB was kind of front and center as well. So now they're also allowing us to tunnel USB 3 traffic across this USB 4 interface. And that's how we're going to see how that's going to work. Now, another thing that the USB 4 they wanted to make sure was added is a standard way of controlling bandwidth. So they wanted to be able to provide a standard way of allocating the bandwidth for different streams of traffic. This is often referred to as establishing quality of service, where you can differentiate and say, this traffic is going to have some certain percentage of our bandwidth, right? And so now we have standard ways of setting that up. That's very important. Anytime you have traffic that's dealing with kind of what they refer to as isochronous transactions, things like where you are streaming video or streaming audio, where the traffic needs to get across the interface at regular intervals, regardless of what other type of generic traffic might be traveling, like PCI Express traffic. So this has been built into the USB 4 spec as well. And they wanted to be able to add all of this new functionality, but they did not want to cause a lot of changes to your existing Type-C port, because USB 3 is its own spec. USB 4 is its own spec. And then the port, the Type-C port, also has its own specification, along with another one called power delivery. So we wanted to create a new USB 4 standard without altering, requiring a lot of changes to some of the existing infrastructure, like these Type-C connectors. That was one of our goals. So if we start kind of from the bottom up and we look at our Type-C, right, the USB-C port, not PCI Express, Thunderbolt 3 had adopted that as its interconnect. Prior to that, it was using a mini DisplayPort connector, I believe. And then Thunderbolt 3 started using Type-C, and it would negotiate to not use the USB 3 protocol, but instead would to an alternate mode, which is Thunderbolt 3. And then it was tunneling PCI Express and DisplayPort. And it liked this Type-C connector because it is a pretty small footprint. If you look at it, it is a very small connector, which is really nice for devices like phones and tablets, which are very thin. It's also one of these connectors that is orientation neutral. It doesn't matter what direction you plug it in, right? There is no upside down, if you want to think of it that way. So that's a really nice kind of feature from a user perspective. They also support passive and active cables. So active cables means that we have some type of signal conditioning that's happening inside the cable. And what I mean by that is you have functionality like retimers, which is going to condition the signal that it's coming in from the port onto the cable. It's going to recondition it for transfer across the cable. And by doing so, it allows you to have much longer cable lengths. So that's already been defined as part of the feature set of this kind of Type-C interface. Now, I had mentioned that this was built, the Type-C interface was built with USB 3 as kind of its native protocol. But another nice feature that I haven't mentioned yet is USB 2 comes free with our Type-C connector, because there's a number of pins in there. We're going to have 24 pins, and there are a handful of those pins that are set aside and dedicated for USB 2 traffic. So regardless of whatever else is happening on the higher speed pins, the USB 2 interface is always there. So that's kind of a nice kind of fallback feature with our Type-C connector. And on the high-speed interface, USB 3 was the standard protocol, but as I mentioned before, it does support negotiating for alternate protocols. And previously, there were two kind of popular alternate modes, as they refer to it. One of them, of course, was Thunderbolt 3, and then another one is DisplayPort. So you could natively send DisplayPort across this Type-C interconnect, which is a nice feature. But now with USB 4, there is another alternate mode, and that is our USB 4 protocol. All right. Several other features of Type-C. It allows for a significant amount of power to be delivered through a little bitty connector. You can now deliver up to 100 watts through that. This is why a lot of the laptop and tablet manufacturers are simply using the Type-C connector as a way of connecting not only your peripherals, like separate I/O devices and hard drives and so forth, but you can also use it to connect your power supply. So you can deliver a significant amount of power through that little port. Right? Now, some of the features I've been mentioning where we are negotiating roles of what kind of mode do we want to operate in, who's going to be the downstream facing port, who's the upstream facing port, who's going to supply power, who's going to be the sink of power. A lot of that needs to be negotiated early on, and that's where that other spec called power delivery comes in. And so there's a whole protocol with this connector for delivering and exchanging power delivery messages for some of that negotiation. All right. So this is what the port looks like. You've probably seen it. It's been fairly popular for the last several years, being included on a lot of phones and tablets and so forth. And you even see it in a lot of laptops, some of the modern laptops. It is this 24-pin connector. It's a lot smaller than the previous USB connectors, the Type A or Type B. A lot of this stuff I've already kind of mentioned, and I'm going to talk about more of this here on the next slide, where we're going to look at USB-C, but we're looking at it from the perspective of a USB 4 protocol, a USB 4 system. So here you would have two separate USB-C ports that you can connect together with a USB-C cable. Right? Now, not all cables are going to be created equally, right? So if you want to be USB 4 compliant, well, then there's certain restrictions that you have to abide by. You can be an active cable or a passive cable and so forth. So there's a lot of requirements associated with the cable. We're not going to get into that here in this session, but we do in our full class. Right? Some of the things that you see here, if you notice, we have a USB 2 host controller, which would be very common in a typical kind of PC or even a laptop or a tablet. So if you notice, I have this wire that's going from the USB 2 interface across the port. So that, as I mentioned before, is always going to be there on Type-C. They're completely separate pins. You will always have that kind of USB 2.0 fallback. These other signals that we see I'm circling right now, those are more of the high-speed interconnect. So you're going to see that we have what they refer to as two lanes of traffic associated with USB 4. And that's because that's what the USB-C connector provides us, is it is going to be dual simplex. So you're going to have two high-speed lanes of traffic in one direction, as well as two high-speed lanes in the other direction. All right, so we can send traffic back and forth in both directions simultaneously. In addition to the high-speed signals, USB-C also provides some sideband signals as well. So these are not high-speed. They're going to be operating at a lower frequency. And USB-C uses this as a way of delivering some of those negotiation protocols at the front. So doing like power delivery and so forth. But we're also going to use this even after the initial negotiation, where we're negotiating what speed we're going to operate at and so forth. We're also going to use this for delivering certain kinds of traffic. So for example, if we are operating in a mode of like DisplayPort, that's going to be our auxiliary link. If you're familiar with DisplayPort, we can have kind of main link traffic, which is where you send your regular data, your video and audio, if you're sending audio via that interface. But the sideband is going to be used or can be used to deliver your auxiliary channel traffic. And then, of course, you have some pins associated with power and ground. And then you have this VCon and this CC, this configuration channel signal. And the VCon and CC, based on how those are connected within the two devices, are they pulled up, pulled down, what size is that pull up or pull down? That's going to dictate who becomes the downstream facing port, who becomes the upstream facing port, and what some of the capabilities are in terms of power that can be provided. So this is just kind of a simple view of this Type-C interface. But another thing that I wanted to kind of show is, if you notice these high-speed signals that I had indicated before, there's a big mux on the front of these. And this mux that's happening on the front of that is showing you the versatility of this Type-C port, because Type-C with this mux, what you can do is, it is of course natively able to send USB 3 traffic. So you can plug in a USB 3 device into this Type-C port, and it should operate natively as USB 3, not USB 4, but USB 3. That's the native mode of operation for that Type-C port. But you can also perhaps plug in a DisplayPort. Now, not the DisplayPort connector that you might be used to, but you can actually plug in a monitor or some video sync where it's using the USB, the Type-C port. Right? That is another possibility that you can have as one of the legs. Right? That's an option. But what we are here to talk about is Type-C now has another use, and that other use is coming from a USB4 router. So that is now going to be our other leg, which we are anticipating is going to be a very popular use of our Type-C connectors, is connecting new USB4 capable devices. All right. So if we spend more time on the USB4 side of it now and look at it from a logical perspective as opposed to just down at the port side of it. So as I was saying, here are our high-speed signals. We're going to group those high-speed signal into lanes. So you're going to have lane 0 and lane 1, and each lane has a signal that's traveling in both directions. So again, you can do this dual simplex kind of nature where you're sending traffic in both directions at the same time. Now, sometimes we get asked, so it's 2 lanes, can you drop down to only 1 lane, or can you implement only 1 lane? The expectation is that all USB4 links should be by 2, meaning that they're incorporating both lanes. The only time we should be down to a single lane is if there is some kind of failure. So dropping down to just 1 lane for a link is considered to be kind of a fallback position. All right. The bottom of the slide here is just talking about some terminology. The link is, of course, the logical connection between these 2 USB4 devices. It's going to be our high-speed signal. The lanes are what make up that link. So you'll have 2 lanes making up this high-speed link. Now, the link itself is going to be flow controlled, like lots of other protocols, high-speed protocols. And in USB4, it is a point-to-point flow control. So before, this device on the left, we'll call this device A, and the one on the right, we'll call it device B. Before device A can send device B actual traffic, USB4 traffic, tunneled traffic, we have to verify that device B has enough receive buffer space to accept it. So the way this happens is there's going to be credits that are going to be exchanged back and forth. All right. Now, this is on a point-to-point basis. If you're familiar with USB4, there's another concept called end-to-end flow control, but that's only happening between domains. I'll define that better here in a little bit. The majority of our flow control is going to be point-to-point, as we see here. There is another type of error detection and correction. So we want to have reliable delivery of data on our USB4 interconnect. So all of the USB4 native traffic, which, as I said before, actually isn't a lot, because most of the traffic that you're going to be sending across your USB4 interface is tunneled traffic. That's the data movement. It's going to be tunneled PCI Express, or tunneled USB 3, or tunneled DisplayPort. And as you can imagine, all 3 of those protocols are standalone protocols. They already have their own flow control. They already have their own error recovery, detection and recovery. And so one of the beauties about USB4 is they try not to complicate that. They say, you know what, if we're delivering tunneled PCI Express traffic, PCI Express already has a very robust error detection and recovery process. There's no need for us to add on to that. I mean, it's already built into that protocol. We're tunneling almost the entire PCI Express packet. We're not modifying that native protocol very much at all. So a lot of that error information, error detection information like CRCs and so forth, is still in the tunnel traffic. So let's just utilize that for error recovery. So your tunnel traffic is relying on the tunneled protocol to do error recovery, which is actually a very clever idea in my opinion. But whenever we are sending native USB4 traffic, which is our control traffic configuring the USB4 systems, those are not tunneling something, so those we do need error detection and error correction. And that is implemented as part of USB4. All right? I had mentioned before that these lower speed signals, they're referred to as our sideband signals. They don't run anywhere near the data rates of our high speed signals, which we're about to see what those are. But the sideband signals are used for our initial link initialization, negotiating what speed we want to run at, and then they're used for some of the management later during runtime. Now, I had said that we have a difference between our high-speed signals and, of course, the others, like our sideband. So what do I mean by high speed? Well, this is USB. So USB is employing the same speeds that we were doing even at USB 3. So they even refer to them that way, right? So we have Gen 2 and Gen 3. So if you're familiar with USB 3, USB 3 started out with Gen 1, that was 5 gigabits per second. Then they had USB Gen 2, Super Speed Plus, which was 10 gigabits per second. And then you had Gen 3, USB 3 Gen 3, which was 20 gigabits per second. We're at the same speeds here at USB 4. But it's a little bit misleading because in a lot of the promotional information that you see, they're always talking about, oh, USB 4 is 20 gigabits and 40 gigabits, which you have to be careful how you think about that, because that is true, but that's not the data rate. What they're doing, if you notice here, the data rate of USB 4 is either going to be 10 gigatransfers per second or 20 gigatransfers per second. All right? That's the data rate. That's the rate at which we're transferring data. So if you are at, kind of the fallback condition where you tried to train to 2 lanes, your regular link width, and something failed on one of the lanes, then your data, or the amount of data you are sending, is only going to be 10 gigabits per second per direction. But where they are getting the numbers of 20 gigabits per second and 40 gigabits per second is they are including both lanes, right? So that's not the data rate, and that's often misunderstood. So keep that in mind. The data rates are still going to be 10 gigabits per second and 20 gigabits per second, okay? Gen 2 and Gen 3 signaling. The other thing you notice here, which we're not going to talk about a lot in this overview section, but is the encoding scheme. So if we're operating at the Gen 2 data rate, the 10 gigabits per second, 10 gigatransfers per second, it's going to use an encoding scheme of 6466. And if we're running at that higher data rate, the 20 gigatransfers per second, that's going to be using a 128, 132 encoding scheme, not 128, 130, which some of the other high-speed protocols like PCI Express use. This is 128, 132. All right, so now kind of working our way up, right? So we started out at the port, right? Understanding what some of those signals were, a little bit about that Type-C interconnect. Then we're moving up to the link, and now we're going to start looking at the devices. So everything in USB 4 is based on routers. Every USB 4 device has to have a USB 4 router. So the router is this kind of green box inside, okay? That's kind of the heart of our USB 4 systems, or any USB 4 device. And of course, we can have different kinds of devices, as we'll see. You can have a USB 4 host, USB 4 hubs, USB 4 peripherals, USB 4 docks, but every one of those kinds of devices have a router. So it's kind of that central logical block, as it says here. All right. Another item mentioned on this slide is a component referred to as our connection manager. Now, I don't want to mislead you. The connection manager is not a piece of hardware. The connection manager is a piece of software. It's the software that is in charge of managing our USB4 interface. And I shouldn't even just say interface, the USB4 system, right? This topology. It's the one that is going to go out and do this discovery and set up all of these devices that we find, all of these USB4 routers, determine what capabilities each router supports, what are the adapters that they have, and then start configuring connections. And that's why it's referred to as our connection manager. That connection manager is going to it's going to interact with our USB4 hardware through a logical block called the host interface. So we're going to see the host interface is a special type of adapter that only exists in a USB4 host. You will not find that host interface adapter in a USB4 hub or in a USB4 peripheral, right? It only exists on the host, right? That's where your connection manager is. Another point is this concept of a domain. So all of the devices that are managed by a single connection manager constitute a USB4 domain. Now, it is perfectly legal to have two separate domains get connected together, but then you have to do domain-to-domain communication. All right, and that's going to be handled a little bit differently than your standard traffic that you are delivering, assuming everything is in the same domain. All right. Another item just to mention, it's not shown here, but just to talk about is, so you can see that we have this protocol where we're kind of daisy chaining devices together, right? These USB4 routers. So it turns out that you can have a maximum of 6 routers connected together in a depth perspective. So if we had, and so what I mean by that is this would be, you know, for example, level 0, because that is where our host is. This would be level 1. This would be level 2. If we had this USB4 connection connecting to another device, another router, USB4 device, that is also at level 1. So I'm not saying that you are maxing out at 6 routers, but what I am saying is you are maxing out at 6 levels of routers, okay? So that's the max that USB4 allows, but you can go very wide, right? Not infinitely wide, but very wide. And so we'll see how that is constricted based on the number of adapters that you can have within a router. So these are some slides that we can go through quickly. That's just talking about what some of the requirements are from a USB4 perspective for these different types of USB4 devices. So one is this USB4 host. So hosts, of course, have to have the host router of this domain. It is also required to have a DisplayPort source, which I found a little bit interesting. So every USB4 host has to have a DisplayPort source according to the spec. It also has to have USB 2 and USB 3 host controllers. So it needs to be able to drive USB 2 and USB 3 traffic. Now again, just pointing out some of the versatility of this interconnect, of this port, is that the USB 2 is always going to be separate from USB 4. So I don't want us to kind of get that confused. USB 2 is always completely separate. It has its own pins, its own bus. It is always independent. USB 2 is never tunneled. However, USB 3 is a different story. USB 3 is going to be this enhanced superspeed host controller right there. And if you notice, coming out of that, some of these ports go directly to the USB Type-C port. So again, you can plug in a USB 3 device into a Type-C connector, and it will operate as USB 3, not doing anything USB 4. And the Type-C port controller is the one that is going to figure out what was connected. Hey, I know we just had an ad, you know, a hot ad. Something was just plugged in. What kind of device is this? So there's going to be some initial protocol at the Type-C interface, right, at that port, using a lot of that low-level protocol to determine what was connected. If it was USB 3, well, then we're going to set up our MUX to bypass the USB 4 stuff, and we're going to send it directly from there. But if what was connected is a USB 4 device, well, then that Type-C interface is going to go to that alternate mode of USB 4. And so then what's going to happen is for that specific port, which has another USB 4 device connected to it, we are going to be tunneling USB 3 through that USB 4 interconnect. We're going to be tunneling PCI Express. We're going to be tunneling DisplayPort. Now that, of course, is assuming that we have devices downstream of that USB 4 interface to consume that traffic. Okay? So here's some of the requirements of our host. Hosts have to support the 10 gigatransfers per second. So again, don't get confused by this. This is actually the 10 gigatransfers per second data rate. That's what that means. So whenever they say Gen 2, that's the data rate. And then the by 2 means 2 lanes. So 10 gigatransfers per second times 2 lanes is where they get the 20 gigabits per second. That's a required thing to be supported. The higher data rate, the 20 gigatransfers per second, is not required to be supported by hosts. That's optional. Okay? That's optional. All right. If we look at a hub, the next kind of device, right? So you can have lots of hubs in your system. If you look at a hub, it has more requirements. So of course it has to have a router, because the router is that central logic. It's the one that is generating or routing traffic in our USB 4 system. A hub only has one upstream facing port, right? So you cannot have, kind of rings or hubs. Everything in USB 4 from a topology perspective is going to be a tree, right? So it's all going to have only one path from any device to any other device in the system. So that means, and one way they implement this is you can only have one upstream facing port. So then you might wonder, well, wait a second, here we have these different hubs in our system and they all have USB connectors on them, right? These Type-C connectors. What if somebody comes in and plugs in a downstream facing port off of a hub to the host? So now we have 2 connections, right? One is connected via the downstream facing port to the host, and another one is connected via the upstream facing port. Our connection manager would detect this when it's going through and discovering the topology, and it's going to disable that external link, that one from the downstream facing port to another downstream facing port. Okay, so that's enforced by software, by the connection manager. Of course, we can have one or more downstream facing ports, right, traveling away from the host. It is required, right, and this is interesting, USB 4 hubs are required to have an integrated PCI Express switch. And this is where you can start seeing the tunneling nature of USB 4. Because what's going to happen is we're going to tunnel native PCI Express traffic. We're going to do very, very little modification to that full PCI Express packet. And we're going to shove that packet into a USB 4 packet. It's going to have like a USB 4 wrapper, but it's PCI Express. And then we're going to deliver it across the USB 4 interface. It's going to be sent to some PCI Express adapter. And that adapter is basically going to strip off the USB 4 wrapper part of it. And then it's going to ship it to a PCI Express component. So we're going to be doing native PCI Express there. It's going to do all of the regular routing that you would do in a PCI Express switch based on, am I doing a memory write or a memory read? It's going to be routed based on address, right? So we have all of these things that are going to be done, just tunneling. And we need our switches and we need hubs, USB 3 hubs as a way of doing that. All right, so USB 3 is going to be the same. Now, what we'll see a little bit later is DisplayPort has never defined things like switches or hubs. So you will not have hubs, or I shouldn't say hubs. You're not going to have, well, hubs or switches as part of DisplayPort. So it will send things natively through from the source all the way to the sink. Okay, but these integrated PCI Express switches and high-speed hubs, USB 3, USB 2, those are required in our USB 4 hubs. So USB 4 hubs are required to support both the Gen 2 speed of 10 gigatransfers per second, as well as the Gen 3 speed of 20 gigatransfers per second. That was not a requirement of the host, but that is a requirement of all USB 4 hubs. All right. And then the devices here, if we look at that one, devices, they have to have, of course, a router. They have one upstream facing port. They are required to support the Gen 2 speed, 10 gigatransfers per second, and it is optional whether they have to support or whether they support the 20 gigatransfers per second speed. Okay, so really the only devices that are required to support that high data rate are hubs, right? That's the only one that is required. It's going to depend on what is the peripheral doing, whether or not it is going to use or need that higher data rate. How much bandwidth does it need to consume? Now, of course, as a USB4 peripheral, there is some functionality of this peripheral. Maybe this peripheral is a hard drive, right? It has an SSD inside. Maybe there's an NVMe controller that is connected via PCI Express. Or maybe it's something else. Maybe this is a display, right? That could be true as well. So whatever the functionality of this device is, you would expect to have some internal endpoint, right? Whatever this I/O device is doing. It might be a single endpoint inside, or maybe you will have multiple as part of a single peripheral device. A very common piece of hardware that we're expecting with USB4 are going to be a combination of a hub with peripherals embedded. So this is a dock, if you think about it. So you would have a hub because there's a single USB4 connection upstream and one or more USB4 connections downstream, right? So that's a hub, but it might also have some integrated I/O devices. For example, because it is a hub, it has to have this PCI Express switch, but maybe this hub also has its own internal Ethernet controller. And that Ethernet controller perhaps could be connected off of that internal PCI Express functionality. So it's seen as a PCI Express device. All right. This makes it a dock, but it does not reduce the requirements of a hub. So it still is required to fit all of the features of a hub, but it's allowed, of course, to have these integrated I/O devices as well. And that gigabit Ethernet, that's just an example, right? You could have lots of other functionality inside these hubs. So moving on a little bit further. So here, adapters are what build, or what are the components within routers. And there's lots of different adapters. All of our adapters fall into three categories. We either have protocol adapters, which are really the main ones. These are like our PCI Express adapters, the USB3 adapters, the DisplayPort adapters. Those are all our protocol adapters. What are we tunneling? What are we sending as our data across USB4? We have lane adapters, which are going to be the adapters controlling the actual USB4 link, right? They have a lot of functionality associated with them. And then control adapters. Every router will have a single control adapter. And the control adapter is what the connection manager interfaces with, talks to, in order to access configuration space of the router. Okay? So the connection manager is always talking to control adapters, because the control adapter is how software, the connection manager, accesses config space of these routers. So here, the protocol adapters, you have PCI Express protocol adapters. So there's two types. You have a PCI Express down and a PCI Express up. And the way this works is if you have a downstream facing port, right, for PCI Express, you're going to have a down adapter. So it's going to be taking the PCI Express traffic, the native PCI Express traffic, and then it's going to be massaging it a little bit and then applying any USB4 wrapper information. That's what the PCI down adapter is going to do. And an up adapter is going to do that as well if it's traffic originating from an endpoint, right, being sent upstream. So that's what the protocol adapter is doing, is it's kind of massaging the native packets and encapsulating them, right, into a tunneled USB4 packet. That's what's going to happen with those. The same is true with USB 3. So we are sending native USB 3 traffic here, right? Native USB 3 traffic here. But as it crosses the actual interface, it's not native USB 3. It's going to be USB 3 tunneled inside a USB 4 packet. And I'm going to show that here in just a second. And DisplayPort's going to be the same way, right? So the DP in and DP out. So a DP in exists and it's associated with a DisplayPort source, the originator of traffic, video traffic, or audio, and or audio. And then, of course, your DP out is going to be associated with the sink. So like a display, right? It's going to be the one that takes the USB4 traffic that has the embedded DisplayPort packets inside it. And then it's going to realign them to the DisplayPort protocol and send it out to the sink. That's the job of a DP out. The control I said already, that's how connection managers are going to access config space inside routers. So the connection manager is going to be talking to control adapters, and there's a whole scheme about how we route traffic through. Inside these control packets, which again are the only native kind of USB4 TLPs, transport layer packets, they're control packets, they have a route string indicating which level am I targeting and then which adapter at that level. But they're always going to go to the control adapter, and then we indicate whose config space it is software is wanting to read or write. Lane adapters are the ones that are controlling the actual USB4 link. So this is where a lot of your flow control is going to happen. Any of your bandwidth management and so forth, a lot of that is going to be occurring at your lane adapters, the negotiation of traffic on the actual link. So by the time traffic makes it to a lane adapter, it has already been massaged from the protocol adapters and then encapsulated within a USB4 packet. And then this is dealing with how do we send this out? What do we send next? Do we have enough buffer space? And so forth. That's going to be handled by our lane adapters. So finishing up, I know I'm getting close to end of time here. Just wanted to show you how important tunneling is to USB4. That really is what USB4 is. It is primarily a tunneling protocol. So it supports USB 3, PCI Express, and DisplayPort, and they're doing so in a way to have very minimal changes to the tunneled protocol. We don't want to require the PCI Express logic or the USB 3 logic or the DisplayPort logic to modify their protocol to work with USB 4. One of the beauties of tunneling is we can use all of this existing IP, all of the existing experience in hardware and software that's been established, been around for a long time, in an unmodified way, and then just have the USB 4 part, those adapters, do the small massaging to get it encapsulated within these packets. So this is what I was trying to illustrate before, where your USB 3 host controller is a regular USB 3 host controller. There's nothing special about it. It's a regular, like an XHCI host controller. It would be perfectly legal, and it's generating USB 3 traffic, right? Native USB 3 traffic. But whenever it goes into this down adapter, that down adapter is then going to encapsulate it. It's going to tunnel that into a packet or multiple packets to send across USB 4. And that's one of the jobs of like a down adapter or any of these protocol adapters is USB 3 has a certain max packet size. That might be bigger than what USB 4 max packet size is. And so that down adapter might have to take a large packet of USB 3 and then segment it up into multiple chunks that it sends as tunneled traffic across USB 4, which then means the other adapter across the USB 4 link is going to have to take those different chunks, those different segments in separate USB 4 packets, and then merge them together into the single USB 3 native traffic again. So that's what we're indicating here. That's going to be your native traffic, right? Until it hits the down adapter is then going to do the tunneling again. And this is all beautiful because we don't have to worry about routing, all of the different routing options of PCI Express and USB 3 and so forth, because we're having native components. We have a USB 3 hub. It takes care of all the routing. We have a PCI Express switch. It takes care of all the routing of PCI Express. All we have to do is get it from the source of the PCI Express across USB 4 to whatever its target is on the other side of the link. It's as if it's going across PCI Express, but it's not. We're tunneling it on USB 4. And then we allow the PCI Express component to do the routing to whatever the appropriate target is, which may have to be delivered across USB 4 again, in which case it would go across another adapter. Okay. So here we're showing the PCI Express side. It's the same concept, right? We have native PCI Express there. It'll be tunneled going across the USB 4 link. And then this logic is going to break it from that USB 4. It's going to unwrap it from that USB 4 packet. and then put it back in the native format, which it really already is. We just kind of take off the wrappers, and then we ship it on to this internal switch. It does all the normal routing based on memory reader write, config reader write, IO traffic message, whatever the appropriate routing for that is, decides the export, the egress port of that switch, and then sends it. If it's going to go across USB4 again, well, then it'll be massaged across to have another wrapper of USB4. And DisplayPort is the same way. The only difference is with DisplayPort, we don't have switches for DisplayPort traffic. There's no such thing as hubs. So if your source is up here, that tunneled traffic is going to remain tunneled all the way through. So it's not going to be, wrapped and unwrapped on every hop of this path, right? It gets wrapped once by the DPN adapter and then sent to wherever the ultimate target is for your DP sync, and it has to go across the DP out. That's going to do the unwrapping and then deliver the traffic to the DP sync. All right. So I know that was a lot of talking. I was talking kind of fast, trying to cover a lot of information in a short time. Hopefully that was helpful.
That's informative and insightful sharing, Joe. Would you like to wrap up with a last message to our audience?
Sure. Thank you, Leona. So if this was interesting and it kind of whet your appetite for USB4, if you would like to have more information about a training class, maybe MindShare could come in and teach a full class on USB4 or USB 3 or PCI Express or any one of the other topics that we teach, you can always contact us or contact Wizlogix, and they will help you get in contact with us for scheduling of a class. All right, so all of our classes are customizable in length and topics.
I hope you enjoyed the session. Thank you so much for all of your time. Thank you so much to Joe for the wonderful sharing today. And thank you for watching. Keep safe, everyone, during this time, and have a great day.